Now, just to reinforce what we should know by now about how you find the minimum or maximum of a y equals ax squared plus bx plus c quadratic function, there are basically two methods for determining the maximum or minimum. They both are equivalent to graphing the function. First, we could complete the square to put the function in the form y equals a times x minus h squared plus k. And in this form, we see that we've taken the y equals x squared graph, we've shifted it plus h units in the x direction so that its vertex, which was 0, 0, goes to h, 0. And then we do a vertical stretch by factor a, which could turn the parabola upside down or leave it right side up, depending whether a is negative or positive, but doesn't affect the 0, 0 point, because all we do with a vertical stretch is move the point this many times further from the x-axis, and the vertex is right now on the x-axis, so that it's not going to go anywhere. Okay, but then we finally add k to the y value we had for a times x minus h squared, and that's going to raise the graph k units so that the vertex is going to move from h0 to hk. So the vertex is hk. Now you should completely understand that, or at least by the time you pull everything in this chapter together, that should be very clear to you. Okay. Alternatively, we can find the zeros and use those to find the axis of symmetry. Again, something you should be quite familiar with by now, but of course I'm going to explain it as we go through it, because I know that most people at this stage are in the process of assimilating all this stuff. Ideally, you would lock this in the first time you see it, the first time you have to use it. Not sure everybody's done the problems yet, so I'm not sure you've had to use it by this point, but that's what you need to do. Okay, so we find the zeros, use those to find the axis of symmetry, and then we can use the axis of symmetry to find the vertex. Very straightforward. Okay. Now, to find the zeros, how are we going to find the zeros of our quadratic function? Well, there are at least two possibilities, and there are other tricks you can pull, but let's stick with these two possibilities. You can find the zeros by factoring, okay, assuming that the function factors and assuming that you can find the factors. Now, in most applications, it's not going to be that easy to factor it. It might not even be possible to factor it. But if you can factor it relatively easily, by all means, you should do that, because it's a little easier than plugging all those numbers into the quadratic formula and simplifying it. However, if that's what it comes down to, that's not difficult, and it doesn't take all that long. You could use the quadratic formula to find the zeros. And there is another alternative, which is to use the quadratic formula to find the axis of symmetry. And you don't even need to find the zeros. And that's convenient because, of course, you don't always have real zeros. Not every quadratic function has real zeros. It can have a graph that lies completely above the x-axis or a graph that lies completely below the x-axis. So a final option is we just find the axis of symmetry. We don't worry about the zeros. We're not really trying to do the whole graph. We're just trying to find the vertex, which gives us the maximum or the minimum, depending on whether a is positive or negative. We just find the axis of symmetry using the quadratic formula. And we really only have to use this part of the quadratic formula. X equals negative b over 2a is halfway between x equals negative b over 2a plus this square root divided by 2a and negative b minus the square root divided by 2a. So the vertex being halfway between the zeros, because the thing is symmetric about the axis, vertex of the axis of symmetry has to be at x equals negative b over 2a. And no, two things. Negative b over 2a is a vertical line. That line is an axis of symmetry. Okay? And there's another thing. Let's see if I can think of what I was thinking. No, don't think so. It was probably something I'd already said. I can't remember what I think it was. Okay, good.